Unit 9 is going to review gas laws with you briefly at the beginning and then apply stoichiometry to those gases. In the past, we have applied stoichiometry to solids. Now we're going to be able to apply it to gases with this part of the unit, and then later we'll apply it to liquids. Just to review, gases, there were 4 variables that we had to be concerned with: pressure, volume, moles, and temperature. Remember, pressure has to do with the particle collisions with the walls or the sides of the container. Volume is the space that it takes up, depending on if it's in a flexible or a rigid container. Moles, this would be the amount of particles that are in there. Temperature is the average kinetic energy, or it's the speed of the particles. We used vectors to represent that as the temperature increased, the particles increased. When you change any one of these variables, it has an effect on changing other variables. And so we learned the gas laws. A couple other conditions we need to remember. Standard conditions, or they call it STP, has to do with pressure units that are at 1 atmosphere, and then we do have those different units for pressure, so we need to be able to convert from one to another if needed. And then temperatures have to be at 0 degrees Celsius, but we have to have them converted to the Kelvin scale in order for our graphs to run through 0, 0. So we have to remember, in any gas laws, temperatures have to be in Kelvin. First law, Boyles Law. Related pressure versus volume. Remember, this one was the inverse relationship. It was the only one that had the inverse relationship. Whereas you increase the pressure, it's going to decrease the volume. You can see my diagram over here. Remember, this one was inversely related. So then we used these charts to put our data in and to calculate what would be the new pressure or the new volume, depending on what they asked. So we have a sealed balloon that is filled with 2 liters of gas at 3 atmospheres. If the pressure is reduced to 0.5 without a change in temperature, what will be the new volume of the gas? So in this problem, looking at what is staying constant, temperature staying constant, and it's a sealed balloon, so we're not going to let particles in or out of it. So initially, I'm going to put my pressure is 3 atmospheres, and I am changing it to 0.5 atmospheres. My initial volume of the balloon is 2 liters. So if I look at, this is from 3 to a half, it looks like the pressure is decreasing. Pressure to volume is a inverse relationship, so the volume should increase. What is the effect if I change one? So to set up my problem, I start out with 2 liters of the gas, because this is what I want to find out, is what's my final volume, times, so I have to set up my ratio so that I get an increase in volume. So I'm going to put 3 atmospheres over a half of an atmosphere. Atmospheres should cancel. You do my math, my answer comes out to be 12 liters. So that was Boyles Law. The next gas law is Charles' Law. This one related temperature and volume. Notice this one is a direct relationship. Look at our graph. So as we change the temperature, the volume is going to increase, so we'd have to have a flexible container, and you can see my signs over here that I used for my arrows to represent that. So here's another example, still using those tables. So this time I have 600 milliliters of nitrogen in a flexible container, and it's heated from 27 to 77 at constant pressure. I want to know what's the final volume, and I did put a note on there, make sure your temperatures are converted to Kelvin. So when we want to convert to Kelvin, Kelvin equals degrees Celsius plus 273. So to mark, my pressure is constant, and I have this in a container that is closed, so I'm not going to change any particles in there. The temperature originally is 27, adding the 273 is 300 Kelvin, and then my pressure or my other temperature that I'm changing it to, is 350 Kelvin. Now, when I add that 273, there's 3 sig figs in that, and there's 2 here. It is going to make those 3 sig figs because that 273 is significant, so we do use it to that. We use the Kelvin conversion for our sig figs on that. And then my volume is 600 milliliters, and I want to know what volume does this have now. So it looks like I'm increasing my temperature, direct relationship, I increase my volume. So if I do my math and set up my problem, 600 milliliters times, I want this to increase, so it's going to be 350 Kelvin over 300 Kelvin, cancels. Doing my math, I get 700 milliliters of the gas. Okay, now 600, since there's no decimal behind that, that is only 1 sig fig, so my answer should be recorded in just 1 sig fig. So we take the one with the least. Gay-Lussac's gas law. This one related pressure and temperature, another direct relationship. Notice temperatures are also still in kelvins. Avogadro's related volume in moles, another direct relationship. I'm not going to work problem for all of these. I think you are pretty familiar with doing these now. Now, this one had to do with Dauntless Law of partial pressures. This wasn't working with 2 variables. It was just working with 1 variable, and it was with pressure. And it also has to deal with a mixture of gases. So what we're saying is, if I had oxygen and carbon dioxide and hydrogen in a container, if I add up the pressure of all of those, it should tell me what the total pressure is. And this is also related to the mole ratio, because pressure is exerted by the number of particles in there. So the more moles, the more pressure there would be. Another example for use of this law is when a gas is collected over water, because when you collect over water, or by water displacement, you're going to have a mixture of gases in there, and that mixture of gases is going to be water vapor and the gas being collected. So here's my example. A mixture of gases contains 0.75 moles of nitrogen, 0.3 moles of oxygen, and 0.15 moles of CO2. If the total pressure of the mixture is 1.56 atmospheres, what is the partial pressure of each gas? So I want to figure out my pressure total. My pressure total, all I need to do is sum up those 0.75, 0.3, and 0.15. It comes out to be 1.2 atmospheres. That's my pressure total of all of the gases. Now, each gas, the one that has the most moles, is going to exert the most pressure. And what it is a ratio of the moles to the total pressure. Whoops, I guess I made a mistake there. This is 1.2 moles for my total moles. I did that wrong. So if that's my total moles, whatever fraction this is, nitrogen, is of the total, that will tell me what fraction it is of, or what part it is of the total pressure. So I'm going to take nitrogen. If I have 0.75 moles and the total moles is 1.2 moles times the total pressure, because whatever part this is of the whole, that should tell me what it is of the partial pressure. This equals 0.975 ATM. So that's telling me what that pressure is. So then I just need to do it for the remaining oxygen. It is 0.30 moles over the total number of moles in there times the pressure of the total container. This equals 0.390 atmospheres. And then for the last gas, carbon dioxide, 0.15 moles. For the partial, over the total moles times the total pressure, it equals 0.195 atmospheres. And all of those added together should equal 1.56 atm. So that would just be figuring out what is the partial pressure of each gas if you know the number of moles. So this is the mole ratio of the partial to the total. That should tell you times the total pressure should give you what the pressure is of each gas individually.